Hello everyone. In today's video, we will be continuing our series of FPGA development where we will be learning about how to implement the two universal gates, that is the NAND gate and NOR gate, on our Shrike-Lite Development Board. Similar to our previous video, here also we will be first doing the simulation using Icarus, Verilog and GTKWave. Thereafter we will be implementing those gates on our Shrike-Lite Development Board. So let's get started. Here I have already written the code that are required for the simulation purpose. First of all, let's study this module, that is the universal gate module. So in this module I have actually implemented both the NAND gate operation and the NOR gate operation using the data flow model of Verilog writing. As you can see, assign NAND O is equals to negation of A and B, assign NOR O is equals to negation of A or B. This type of assignment operation or writing in Verilog is known as data flow modeling. So for seeing our module in work, I have also written the test bench for this module. So as you can see, the time scale, this command means that we are mentioning the scale as nanosecond, 1 nanosecond scale with a precision of or resolution of 1 picosecond. Here, like in our earlier video, I have used the dot operator for instantiating our design under test, that is in this case this module. However, in this scenario I have not used that. Rather than using the dot operation, I have maintained the sequence in which the like input outputs are mentioned here. Suppose here, as I have written in 1, in 2, out 1, out 2, instead of that, if I have written in 1, then out 2, then out 1, then in 2, what would have happened is out 2, this signal would have latched with this signal, like get connected with this signal. What will happen if we do that thing? Our simulation result will be wrong, because here we are actually changing the values of inputs in 1 and in 2. However, our simulation will show that we have no change in value for this out 2, which is actually being treated as an input to this module. As a result, we have to maintain the correct sequence of the ports for our design under test when we are not using the dot operator. However, if I use the dot operator, then it doesn't matter how I am going to write the ports in sequence. So here we have our initial block. I have discussed all these things on our previous video. This dump file means like generation of the .vcd file, and dump vars means 0 here means all the variables, and from which module? From this test bench module. We are actually going to dump the values of these variables from our test bench module. So let's quickly go to our simulation part. We have the universal gate TBN. So I will be using iVerilog or Icarus Verilog, as we know. iVerilog universal gate, our first file. Oh, 1 second, I forgot to mention the output file. Output, we already do have a output file named as output, so let's just name it output. Let's keep it as output only, so this output file will get overwritten. Let's mention our Verilog modules, universal gate tb.v. We got one error, that is the here, as we can see on line number 1. Let's just visit our line number 1. I have used a wrong symbol here. This should have been this. So as you can see, if we have any error, Icarus Verilog will actually throw the line number that is line number 1 as we got, and it will show the error. In this case it was a syntax error. Again, let's compile it. We got our file, then we will run vvp output. We got our .vcd file. Let's run the GTKWave, that is universal gate dot gates dot vcd. Input 1, input 2, output 1, output 2. As you can see from here, we have both input 1 and input 2 as 0 0. Here out 1 refers to NAND and out 2 refers to NOR. So when both are 0 0 0 NAND we are getting 1, NOR we are getting 1. For 0 1 input combination we are getting NAND as 1, NOR as 0. For 1 0 input combination we are again getting NAND as 1, NOR as 0. And for both 1 1 input combination we are getting both the NAND and NOR as 0. So from this simulation only you can see that we have successfully verified our design, and our design under test, that is the universal gate module, is actually working perfectly as it is supposed to. So let's move towards the FPGA development. Let's continue with our FPGA development. We have the GOS configure software. Let's start a new project. First of all we need to select our part. Let's name it to NAND gate. We have the test Shrike here. Set the values to the first upward arrow value. Click on apply. OK. Let's focus on our FPGA core. Again, as I have already discussed about the procedure for writing this Verilog code for the Renesas FPGA, I am not going to discuss again. But in short, this start top star actually refers to the synthesizer that we are using this module as our top module. NAND gate, we have input A, B, output C. Again, we need to mention the C enable. Let's enable C enable as, let's set that C enable signal as 1. Then we will be assigning C as negation of A and B. End module. Let's just save. Click on synthesize. Synthesizer is complete. The network is combinational, that is the warning we will be seeing. Now let's head on to the IO planner. We have GPIO 0 in as our A. We have GPIO 1 in as our B. We have our GPIO 2 out as C and output enable as C enable. Let's click on save all. Generate bitstream. Yes. So while the bitstream is being generated, let me explain you once again why we need this C enable or this OE. So in our Renesas FPGA, that we are having in our Shrike-Lite Development Board, the output or input are being driven from the same GPIO port only. So to have a particular port as an output, we need to provide a signal named as output enable. If that output enable signal is high, then only the GPIO port will act as a output port. Otherwise, even if we try to mention the output at a particular GPIO without mentioning the output enable pin as high, we will not be able to have the output from that particular GPIO. So as you can see, we have some of the issues. Let's just see the issues what we got. That is, the network is purely combinational. Again, we know that we have some potential interface timing issues. Yes, as we don't have any kind of clock dependency, so the synthesizer is telling us that we might have a potential timing issue, which is not a problem for our combinational logic circuit. Here, as you can see, we have the netlist generated. This is the post synthesis RTL that is being written by the synthesizer. This is the floor plan, as you can see. Again, that same floor plan. This is actually being mapped. We have the synthesizer report, the amount of constant that our FPGA is actually using, 4 wires, 4 wire bits, 1 cell, 1 LUT2. As LUT lookup table, as we know, lookup table, we are using a lookup 2 variable lookup table. We are using a single gate, so there is only one lookup table. Resources report, this is the amount of resources we are actually using. Again, RTL input ports 2, RTL output ports 2, GPIOs, obviously we are having 3, that is the input A, input B and output C. Output enable will not be considered as an output, though we can see, like, there is a slight confusion that might arise. We can see that there are 2 RTL output ports. Yes, we have mentioned C enable as an output, but in general we are not actually using that C enable to to provide any output. So here we are actually seeing only 3 GPIOs, that is the A, B and C. So in this way we will be designing similarly our NOR gate also. So let's just close this. We have the FPGA core, this one. So let's just create our NOR gate also. Here I would like to mention one thing. I just forgot to write one extra part, without which the FPGA won't be working. Let's just correct this thing. IO pad external pin. This means we are actually providing the input or output from outside. I will be correcting this for the NAND gate also. Let's just do this. Input B, output C and output C enable. I forgot to write this for the NAND gate. I will be doing that also. assign C enable equals assign C equals A or B end module. See, for the let's click on synthesize. For the NAND gate that we wrote earlier, we didn't get any kind of error because this is not a syntax error for Verilog. It is actually a mentioning that we need to like a part of mentioning that we are actually going to provide these signals from the outside. Like we are going to provide the input from the outside, the output C enable, that is this writing this will actually map the output signal to an external GPIO directly, otherwise it won't. Again we are having the same A B C, and here we got the C enable. Let's click on save all, generate bitstream, save yes. Let's just wait a few seconds. Here, this is the NAND gate part. Let me redo this thing also. Input A, input B, output C, and output C enable. Again save this. Let's click on synthesizer, generate bits. Do we have the IO planned? Yes, we have the IO plan. Generate bitstream. Let's check our NOR gate. Yes, we have the PNR completed, 0 errors, 4 warnings and 1 warning, total 5 warnings found. This is the netlist for the NOR gate that is being generated by the synthesizer. Post synthesizing RTL, this is the floor plan for the NOR gate. As you can see, we have the resource report. This is the total resource. This is exactly similar to that of the NAND gate only. So we have the NOR gate. Let's close the NOR gate. This is the NOR gate operation. Let's close it. We have generated the bitstream for the NAND gate. We have fixed the issue that we earlier had. Let's close this one also. So we have created both the bitstream for NAND gate and NOR gate. So we will be seeing the NOR gate and NAND gate operation on real-time signal on our FPGA. So here we are on the Thonny IDE. We have already connected our development board. As you can see, RP2040, it is connected. Let's just upload our binary file that we have generated. Here, as you can see, let's first test with the NAND gate. NAND gate. The MCU bin. We will be overwriting it, the already existing binary file. Let's just wait for some time. It's actually being uploaded. So upload complete. We have the main.py. This code will actually we will be using for flashing our Shrike-Lite. Let's just flash our FPGA and it's done. So now we will be actually testing our code with real-time signal on our FPGA. Before going to the FPGA, let me just quickly show you the actual schematic, like the schematic that I have followed. This is the NAND gate representation using the FPGA. We have the NAND gate, along with which we have connected two inputs, input A and input B, which are basically being grounded such that the signaling is always 0. That is, the by default input should be 0 0 to both inputs, and we have an output LED here. So as soon as we press the inputs using the push buttons, we will be having the corresponding output result on our FPGA output. Now for this, as we can see, we have the input. Let's just see the input. This is the input A, and this is the input B. The green light is the output. So according to NAND logic, 0 0 gives us 1, 0 1 gives 1, 1 0 gives 1, and 1 1 gives 0. Again 0 0 gives 1, 0 1 gives 1, 1 0 gives 1, and 1 1 gives 0. So as we can see, we have implemented a basic NAND gate on our FPGA. Okay, now we will actually be uploading the code for, like, the binary file that we have created for the NOR gate. Build. Let's just upload it. Wait for some time. If we want, we can actually change the binary file name, but if we do so, we do have to change the file name here also. Let's run on the script. Our FPGA is done programming. So again, we will be testing it with real-time signal. Let's go to the development board. Now this is the schematic that I followed for the NOR gate operation. Pardon me, I have written NOT gate. It should be NOR gate. Again, both the inputs are connected to ground, such that the default signal that is being provided to the input ports is 0. Now let's focus on the real-time implementation. Here you can see I have implemented the logic connections. Now for NOR operation, we know this is the input A, this is the input B. Now for the NOR operation, we know for 0 0 we will get 1, the output LED is high. For 0 1 operation, we will get 0, the output LED is off. For 1 0 input, output is 0. For 1 1 input, the output is again 0. So as you can see, we have also verified the basic NOR gate on our FPGA.